Okay, does it work? 1, 2, okay. Thank you for the introduction. So, unfortunately, we had to change the format. So, what we wanted to do initially was to talk about the status of AI in New Zealand and what are the challenges. Unfortunately, apparently, we came up late with this idea. So although we managed to squeeze into the program, we're not able to do that. So for that reason, I'm actually going to give you NVIDIA's perspective and what NVIDIA is doing for AI for science. And I hope you're going to participate and tell some of your stories. Apparently, we have a whole hour before we are supposed to go for dinner. So I hope there will be some discussions later on. So, what is generative AI? Again, I want to make a distinction, and April mentioned this about the talk this morning. There are multiple fields, and there are actually some overlaps when we're talking about machine learning, statistics, AI, deep learning. But generative AI, it's all about generating new data based on any type of input. And again, most of you, and this was popularized by ChatGPT, and a lot of people, when we are talking about generative AI, they only think about chatbots. But generative AI, it's a lot more than that. You can actually have anything in the input. You can have images, you can have text, you can have videos, you can have molecules, you can have proteins, you can have anything in the input. And then you have a large language model. And then that large language model, again, can generate any type of output. So you can have images as input, and it can generate text. You can have proteins, and you can generate new proteins and new molecules. The point being is it's not just chatbots, and it's not just ChatGPT when we're talking about generative AI. And as you can see, there are multiple fields where generative AI can actually be applied. So there are a number of domains. The first one is text generation. And again, this is what popularized the whole field of generative AI through ChatGPT. Now you have Copilot, you have Gemini from Google, you have DeepSeek from the Chinese company. You have a lot of models that are falling into that category for text generation. And there's a nuance for that for translation. Again, there are multiple models that are being used for translation. There are a lot of, again, specialized models that are being used for coding. And again, this is becoming more and more popular. If you're an RSE, as we were talking earlier, you will be getting a lot of help in your work through these new models that are able to basically generate entire snippets of code. It doesn't mean that these tools are going to replace you. These new large language models are going to replace your role, but it will help you tremendously in generating the code for you. And then you will still have the domain expertise that will help to actually incorporate that into a specific workflow. Visual content, again, the entire media and entertainment market, it's crazy about the possibilities that are being opened by generative AI. And life sciences, again, April mentioned about AlphaFold. I'm going to bring a couple of other examples. So again, the industries and the domains that are being transformed are basically countless. If you look across it, I'm not going to go into every single box there, but as you can see, no matter what area you're looking at, and I know this is a research conference, so you can think at basically the research that goes into every single domain there, every single industry, the research that it's being done there can and will be augmented by generative AI. So generative AI is a journey. As I said, for most of the people, it actually started when ChatGPT first published ChatGPT. For us at NVIDIA, we've been working on large language models for way longer than that. And we've been investing in different technologies, both hardware and software, to make sure that we can accelerate the next generation of large language models, no matter how these new models will look like. Even with the advent of the GPT models, we already had in our low-level architecture capabilities to actually accelerate, for example, the transformers, which is a component that was popularized by Google, again, way before ChatGPT even became a thing. So we are part of this journey, and we are trying to move as fast as possible. We like to say that we're moving at the speed of light, but for the researchers and the vast majority of the community, this has been a journey. And it started, as I said, when ChatGPT was announced. Then in 2023, there was a lot of experimentation, and there's still a lot of people, actually even in 2024 and 2025, there's still people at that first initial stage, and there was that question, is it a hype or not? I don't think it's a hype. It's just that at this point in time, a lot of people are trying to figure out how they can use this technology. And as I said, I think the possibilities are actually endless. You just need to figure out how you can apply that to your workflow. And I'm going to show you a couple of specific examples. And then productizing and embedding this results and science into the actual application. And you've seen the domains, once again, are countless. There are actually different entry points. And again, as a researcher and a practitioner, you need to understand that not everyone will start with a foundational model, with a frontier model of trillions of parameters and trying to train that from scratch. There will be a number of companies around the world, yes, who will be doing that. Again, April mentioned X. We're working with their XAI branch, and they have 200,000 GPU systems to train their Grok model. We are doing the same with OpenAI and a couple of others, but it doesn't mean that everyone will actually be at that entry point. Yes, there will be new frontier models that will be popping up here and there. There was a lot of hype recently about DeepSeek and the work that was being done around DeepSeek, but the vast majority of the people will be at one of the other stages. They will either take a model that has already been trained and you're doing fine-tuning or parameter tuning, or you're just merely using one of the models that has already been already fine-tuned even, and then you're connecting that with your own database, and you're utilizing the capabilities of the large language model in conjunction with your own data. So there's actually an entire workflow. If you look from the data preparation, training, and customization, all the way to deployment. A lot of people at this point in time, again, they're way too focused on the model customization and the training or the pre-training. But there's a lot of work that needs to be done. And actually, there was a very interesting talk this morning about how do you curate the data, and is that data actually relevant? Is there any bias in that data? Let's say you want to build a model for the Maori language. Do you actually have a good enough data set to actually train or fine-tune a model with that initial data? So again, there's a lot of work that is being done both on the data acquisition as well as the data curation. Generating meaningful data that you're actually putting into your large language model, it's a science in itself. And there's a lot of work being done there, both at NVIDIA as well as around the world in terms of both research as well as on the enterprise side. Pre-training, again, as I mentioned, there's a lot of work and optimization that is currently being done. Once again, DeepSeek has been in the news for not necessarily pre-training, but training their model. There's still a lot of work and a lot of the optimization that can be done at the large language models that are still untapped. So there's a huge research potential that can be done there. Model customization, again, this is more on the taking a model that has already been trained and you're simply fine-tuning that model. Information retrieval, or RAG, retrieval augmentation generation, is basically the idea of connecting your large language model with a database which is proprietary to your enterprise, or is proprietary to your, or is specific to your domain. And you don't need to train from scratch the entire large language model. You can actually use information retrieval to augment your model with that data. Oops, sorry. And the last part, you actually need to do something meaningful with that model. Once again, there's a lot of hype and a lot of discussion about training and what are the requirements to train a model. There's less discussion about the inferencing part. And actually inferencing, on the long term, it will actually require even more compute capability, as well as more innovation to make sure that inference is being done in a meaningful way. And when I'm saying meaningful way, we are already talking about agentic AI. You have multiple AI models which need to interact with each other. How do those models interact? What are the limitations? What are the capabilities in order to, for example, to provide a timely response? There needs to be millisecond interaction or microsecond interaction between all those agents to actually provide a timely response. And last but not least, guardrails. You don't want the model to speed out sensitive answers. You don't want the model to go beyond what was actually trained or meant to do. So what do you actually, what are the requirements to build these custom LLMs? Obviously, training data, and you require a lot of it. It can either be data that is available, or you can, again, use large language models to generate more data. And again, we, both at NVIDIA as well as around the world, there's been some research done. How can you use large language models to actually augment and generate additional data when you don't have enough data for your models? Accelerated computing, I think many of you here are part of the HPC community, as myself. You need a fairly significant infrastructure to do that, and April again talked about this. Here in New Zealand, NeSI is at the forefront of providing these capabilities, and I think in the near future or mid-future there might be others providing this kind of capability. Training and inferencing tools, this is the software that comes with it, and last but not least, the AI expertise. And I know there are a couple of talks these couple of days about the training, the workforce, and the capabilities required for that. I'm not going to go into all the details, but the long story short is that across this workflow that I just mentioned, NVIDIA has been innovating either ourselves. We actually have an NVIDIA research arm. I don't know how many of you know that, but NVIDIA has its own research arm. And most of the engineers at NVIDIA are actually software engineers, not hardware engineers. So if you think that NVIDIA is just producing GPUs, you're very wrong. We are doing a lot more software innovation these days than hardware. So there are a number of components. For those of you who are practitioners, I highly encourage you to take a look. There's a toolkit called NeMo that integrates components for all the different parts of the workflow that I just mentioned earlier. And just to give you a couple of examples where NeMo and large language models are used across the industry, I'm going to skip very quickly through this, and I'm going to focus on the science part. But once again, the reason I put this in, so this is ServiceNow, this is SAP. You're probably familiar. You might have this as your ERP component in a university or lab. MDocs. This is cybersecurity. Here we are not allowed to mention the actual company, and even ourselves, we're actually using large language models internally. We have designed a large language model called NeMo, Chip NeMo, to actually help us in designing our own chips. So again, how do you get started? Identify what is the thing that you want to solve with generative AI. build out the domain and AI teams. A lot of people start to think, oh, we should be putting or we should be using generative AI in our work, but that's not it. You actually need data scientists, you need data curators, you need a lot of capabilities to actually get this started. Analyze the data for training and customization, invest in the infrastructure, and last but not least, develop and plan responsible AI. Again, April mentioned there's a lot of regulations being put in place, especially in the European Union. We see less of that in Asia Pacific, but I think things will change soon. So I'm going to skip this again in the interest of time and go into how this actually applies for science, because I think this will be very relevant for the audience here. I provided an outlook of what we are doing in general in terms of generative AI, but now I'm going to focus specifically how this will apply for scientific computing. There are a number of domains where we've seen generative AI already being applied. And this work is actually part of the Gordon Bell Award. I'm not sure if you're familiar with this. So Gordon Bell Award, it's like the Nobel for computer science. And tomorrow morning, I highly encourage you to listen to the keynote, because one of the professors, Giuseppe Barca from University of Melbourne, is actually delivering a keynote exactly about this work, for which they actually won the Gordon Bell Award. So again, it goes from molecular dynamics to genetics, protein design, weather and forecasting. So again, this is more like an ad for tomorrow's talk. I highly encourage you to join Giuseppe's talk tomorrow morning, the keynote. And speaking of Nobel, there's actually the actual Nobel Prizes. Last year, because we're already in 2025, the prizes for physics and chemistry have been awarded for work around AI. And specifically, the Nobel Prize for Chemistry was awarded for a tool called AlphaFold. Is there anyone here using AlphaFold? Okay, a couple of you. Good. So you probably know those guys. Those are the ones who actually put together AlphaFold. NVIDIA was involved in the effort to actually make AlphaFold working on our GPUs, and we're still providing support to accelerate AlphaFold and a couple of derivatives of AlphaFold on our GPUs. And we actually have some successful collaboration. I'm actually open to have a discussion later on about this. We have a very successful collaboration, very close here in University of New South Wales. Professor Kate Mitchell. Yeah. She's doing really great work with AlphaFold, and that's really interesting. So the point that I wanted to make is, again, AI for science. It's here to stay. We're seeing applications across a wide range of domains. For example, I'll pick on seismic, because I talked about a couple of other things already. In seismic, for example, when you're talking about reservoir simulation in oil and gas, a lot of oil and gas companies are looking at how do they actually define the reservoir in order to know where to do the drilling. In order to do that reservoir simulation, historically, most of the work was traditional CFD, where you're solving partial differential equation to actually define that the size and the shape of the reservoir simulation. With the new advancements and with generative AI, you can actually use what we are calling PNNs, physical informed neural networks. And this is a new class of AI models that can actually, based on on specific input, they can actually learn how to solve those PDEs systems without actually doing the mathematical computation. And we have a tool, so this is being distilled, again, there's an entire research field around this. This is being distilled in a tool called Modulus. And Modulus is actually the foundation for a lot of CFD simulations where AI is actually employed in, to solve those mathematical equations. And this has application in seismics. It has application in weather. Again, we are doing some work with, and I'll show another slide later on. We're doing some work in climate and weather forecasting, where we can actually use AI to do both weather prediction as well as climate simulations at different scales, whether it's regional, global, short-term, like no-cast, as well as long-term, years and decades. So one of the things, and this was announced very recently, that's why I wanted to put it in here, because maybe, I don't know if you're familiar with this. Is there anyone working on material science here? Nope? Okay, yeah. Exactly. So try to spread the word. So material science, again, it's a very difficult domain, because when you're trying to discover new materials, you actually need to do thousands of experiments on combining different elements to actually come up with a new material. So there are trillions of possible combinations that one could potentially or would need to try to get up to a new material. So what we are trying to do here, we've launched this at Supercomputing in November last year. This is a new tool which is specifically for this material science domain. It's a new model that has been trained on a data set of, I think, 2,000 materials. It doesn't say here. Well, it's 60 million. These are all the possible combinations, but the database on which it was it was trained, it's actually much smaller than that. But those are all the possibilities that normally the model should actually try to look at. So we've been training this model to actually be able to come up with new materials based on several constraints. So again, if you have any peers working in material science, we are really interested in collaborating in this topic. So obviously, a lot of acceleration through this. I was mentioning earlier climate and weather. This has been a project that NVIDIA has been working for almost 2 years now. And there are two components here. First of all, we came up with Earth-2 is basically the name of the entire project. And there are two components here. First of all, you have ForecastNet. And ForecastNet is, again, a neural network that allows you to do climate simulation at the global level. Based on the historical data, you can actually do prediction at the global level, but that doesn't provide you the accuracy that is required, for example, if you want to zoom down at the regional level. So let's say at the islands of New Zealand. We're actually building a new capability called CoreDiff, and we are working actually with both Forecast and CoreDiff. With the newer guys. Hopefully you'll be able to, maybe next year, to hear a bit more about how this is being used at NIWA. CoreDiff, what CoreDiff allows you to do is another class of AI models that is taking regional data from the Met offices, and it's allowing you to downscale the climate simulation all the way down to the city level. And we've demonstrated this. You can actually look online. I should have included the video. We have this demonstrated both in the US as well as with the Taiwan Met Office, where we're showing how we can actually downscale the climate simulation all the way to the city level. So obviously, accelerated computing is here to stay. In order to do all those cool stuff, you would need accelerated computing. And again, it's not just NVIDIA saying this, it's not HP saying this. So yes, you might see us as vendors, but we are working, NVIDIA is working with the research community. This is what the researchers are telling us, that in order to do their life work, they actually need accelerated computing. If you're looking at this, the statistic of the top 500, and again, those of you working in HPC might be familiar with this, top 500 is actually the ranking for the most powerful 500 supercomputers around the world. You can see that the number of computers in the top 500 that are accelerated is actually grown tremendously over the past couple of years. And just to put it in perspective, these are all the systems that are going to come online that are at least half of an exascale size, and that means hundreds of nodes, if not thousands of nodes, only this year. So again, we are talking about massive capacity that's being built around the world. And the point that I want to make here is that the workload is changing. As April was mentioning, we are no longer just talking about traditional HPC. We're talking about HPC plus AI. You've seen, we've been talking about AI for science. There's quantum computing, which is bringing a new type of workload, and there's interaction between classical computing and quantum computing. So all these are becoming new workloads for these new systems. So when you're looking at the scale, it's not, these systems are not built just because they actually have enough budget to build them. Yes, you need the budget to build them, but there is actual workload and there's actual demands for such systems. So getting back to the previous question, there's definitely not hype. There is real needs in the scientific community to actually have systems of this size to actually be able to solve some of those challenges. So this is a shameless ad. In about a month, NVIDIA is going to have our biggest conference called GPU Technology Conference. I highly encourage you to register. There's going to be a lot of session. Even if you cannot attend in person in the US, I think 3/4 of the sessions are actually recorded, and you can see them either live or recorded after the event. There's a lot of technical content. As the name says, GTC actually stands for GPU Technology Conference. So I've been attending that conference even as a researcher. So I'm coming from a research background. I attended this conference as a researcher. There's a lot of really good content in there. So with that brings me to the end of my presentation. I hope I'm on time. So thank you for listening, and I'm happy to take some questions and have some discussions. Any questions, comments? Yes? Can I have the mic?
Great, thank you. We're going through lots of changes every month with terms of the compute power and the software and all that. It's hard to keep up. Is it going to be that again when quantum computing comes along? Is it going to change the game again is it going to be utilized by GPUs? We have to upskill again? Is this going to roll on forever, just learning about software stuff? How do you see it? Yeah.
Actually, you're not entirely wrong. So there is a lot of work that is being done now. So first of all, we are not going to have a viable quantum computer in the next couple of years. There's still quite some time until we actually get a quantum computer that can do some meaningful work for us. What we are doing right now in the space of quantum computing, there's a lot of simulation that is being done, and that can be accelerated by GPUs. In terms of catch-up work, there's actually, I would say, some work being done right now where multiple companies, including NVIDIA, we're looking at creating a framework that can express algorithms and describe problems in a way that can run both on a classical computer as well as on a quantum computer. And even when the first, and there are already a couple of QPUs, quantum processing units. Those, we are seeing more and more those attached with GPUs, and you'll be able, soon enough, the same algorithm, which is written in that language, right now it's called CUDA-Q, you'll be able to run that both on the GPU as well as on a QPU. So hopefully you're not going to need the same upskill that was required to use accelerators. And then, yes, to the comment, there are a number of research initiatives where AI would potentially be used to either generate efficient algorithms for the QPUs, or and there's quite a number of things that need to be done on the QPUs, like error correction and a couple of other things, where, again, AI can help with that. But in terms of upskilling, I would say that there's work into that direction, as I said, to potentially have a higher level language that can describe the algorithm for both accelerated computing as well as quantum computing, so that you don't need to do that upskilling once again once the QPUs become viable.
Great, thank you.
Any other questions?
Not so much a question as an observation that, you know, more than 15 going on to 20 years ago, a little cluster that's like I was involved with had a couple of GPU nodes, and of course at the time we didn't use it for much because the software wasn't available for it, and that's I think that's like what we can make an elaboration. Is I think what we've really seen is in recent years, not only have we seen the hardware developments, but finally the software has come of age as well, and that's actually like the thing that's been holding things back, I think, for a long time in the GPU world. It was, really a case of trying to find a little bespoke applications in which you could actually send stuff off to the accelerator, and it's basically built up over time. I guess another thing that I want to make as an observation, which is an aside, but follows on from your previous questions, I think we really need to be consistently aware of the difference between quantum computing, which is a fairly well-established practice, and quantum computers, which are a very, very different kettle of fish. And I suspect we're going to see the former doing real work a long, long time before the latter.
Yeah. Well, on the first question, I totally agree. I started in 2008 with GPU computing, so I was actually programming with CUDA version 1 at the time. As I said, I was a researcher at the time, and obviously over the past 17 years, the software came a long way. It required a lot of tweaking at the time to be able to run on the GPUs. Nowadays, a lot of these things are actually being abstracted. I would say most of the data scientists, if you look at the entire pipeline and workflow that I was presenting previously, they don't even need to know that it's actually running on the GPU. You're just running a container, you have an environment, and it simply runs. Yes, there will be some guys at the back end, the sysops and the DevOps who need to make the magic happen. But from a researcher perspective, from a practitioner, you don't actually have visibility, or you don't need to know what's happening at the back end. And again, yes, there's a lot of investment, and even NVIDIA has come a long way from where we were when we first introduced the first programmable GPU. And second comment on the quantum side, yes, quantum computers are basically reshaping the way you think about algorithms. There's no longer 0 and 1s. I think everyone understands at the very basic level that quantum computing is no longer zeros and ones. But in order to achieve computational capability that can actually describe a meaningful problem, yes, there's still a long way. Saying that, quantum computing, it's here now. We are doing a lot of collaborations across the world. Again, if anyone is working in the realm of quantum computing here in New Zealand, I would be very interested to talk to you. We're doing a lot of engagements, again, from Australia, Japan, US, Europe, pretty much all over the world. I think someone mentioned in the morning session that there are initiatives here in New Zealand around quantum computing. I'll be very eager to learn about that. So if anyone has any leads, let me know.
I remember talking to Lev about 10 years ago at eResearch in Melbourne and wondering when the singularity was going to happen, and we were predicting 2034 or something like that. So.
Yeah.
Am I going to win my money on that one or lose it?
Which way did I bet? Did I say before or after?
I think other people were arguing 2048. But,
Okay. Any more questions? As I said, I hope to have this interactive. We still have 20 minutes before going for dinner, so. Oh,
Drinks. There was
well, drinks is on HP, and dinner is on us tomorrow.
So I saw in one of your slides you mentioned there was just on the bottom the Grace Hopper and that AI being incorporated into the supercomputing, giving you 2 times the energy efficiency. Because I often hear energy cost as being part of the discussion. So do you have any comments or anything that you could sort of speak on that topic?
Oh, a lot. I can talk for another 2 hours on that topic. So I didn't want to focus at all on the hardware. I was talking about the vision of software mostly, and how is NVIDIA looking at AI for science. But yes, energy efficiency is definitely at the core of basically the entire work that we are doing from the chip design. And when I'm saying chip design, yes, we design GPUs that are consuming more power if you're just looking at the data sheet. And again, April made a very good job saying that, oh, the NVIDIA GPUs are going to consume 2,000 watts. Yes, they will, but they're becoming a lot more efficient. So basically, if you look in perspective, in order to execute the exact same job on the newer GPU that consumes, let's say, twice the power, you can actually do that 10 times faster. So actually, the energy efficiency is much better than on the previous generation. So for example, when you have GPUs from a previous generation, you're actually much better off replacing it with newer ones, even if it's a smaller quantity, because they're actually more energy efficient than the previous one. So these are at the very generic level. And then we build on this capability from the GPU side all the way to the system level. We are doing optimization. For example, we are interconnecting the GPUs with a proprietary communication protocols called NVLink that allows you to pull together the amount of memory. Then we are doing optimization at the system level, at the data center level. So right now, all the designs that we are doing are actually at the data center level, and we are looking what optimizations we can do at the data center level. On the particular topic that you mentioned, Grace Hopper, that was on my slide, that is, again, yet another initiative that NVIDIA is doing. We're basically looking at how we can integrate both the CPU and the GPU in a unified package and form factor. I don't know how many of you are aware. Again, NVIDIA is not just doing GPUs. We actually have our own CPU. It's an ARM-based CPU, and we integrate that together with the GPU. And we don't do it simply because we don't have anything better to do, but there are a lot of options and capabilities that arise from that. One of them being, for example, just to give you a very short example, in an x86 plus GPU, you have the total power for the GPU and the total power for the CPU. And you can only vary slightly the power on the GPU, and you can slightly vary the power on the CPU. In the Grace Hopper design, where you have both of them working basically as an SoC, you can actually steer the power, so you can actually take more power from the CPU which potentially is underutilized, and move that to the GPU, or the other way around. If the GPU is underutilized, you can actually steer power from the GPU to the CPU. There's no way you can do that unless you have a tightly coupled and tightly integrated design like in the Grace Hopper. So Grace Hopper, yes, it's in itself, it's a step towards energy efficiency. And as I said, it allows us to do things that otherwise wouldn't have been possible in a traditional x86 design.
Thank you. Any further questions or comments? Any discussion? Well, if not, then please join me in thanking Gabriel, and we will probably have you'll be around if people want to come up for discussion.
The next couple of days until Thursday, so
excellent. Thank you.
Happy to take any further questions. Okay, thank you.